Visible machinery grinding beneath everything you have ever seen. Planets move because that machinery tells them to. Stars live and die on their schedule. Your heartbeat quietly obeys it. We like to believe that machinery is stable, predictable, safe, but scattered across the cosmos are places where that illusion starts to tear. Environments where gravity becomes monstrous, where matter is squeezed into forms no human has ever touched, where space and time stop behaving like the quiet background you grew up with. These are not glitches. They are the places where physics reaches its limits. Some of them we have seen with our telescopes. Others lurk only in equations that have never failed us in the lab. Yet they all sit exactly where our best theories begin to contradict one another. Alright, let's get into it. Number 10. The surface of a neutron star. Imagine taking Mount Everest and crushing it until it is no larger than a grain of sand. Even then, it would still be less dense than the matter on the surface of a neutron star. This is one of the few places in the universe where ordinary intuition completely stops working. Neutron stars are born in supernova explosions when massive stars run out of fuel and their cores collapse. What remains is roughly the mass of the Sun compressed into a sphere only about 12 miles across. A single teaspoon of this material would weigh billions of tons on Earth. Under such crushing pressure, atoms fail. Electrons and protons are forced together, creating neutrons. The familiar structure of matter disappears. Chemistry ceases to exist. Physicists think the outer crust forms an exotic crystal lattice, while deeper layers may contain forms of matter no Earth laboratory can reproduce. Here, quantum mechanics, relativity, nuclear physics, and gravity all collide at once. Despite decades of research, scientists still debate what truly exists inside these objects. It is like descending into an ocean where every mile of depth rewrites the laws of water. The deeper you go, the less recognizable reality becomes. And the disturbing implication is simple. What we call normal matter may not be the default state of the universe. It may just be one fragile arrangement among countless possibilities hidden in the dark. Number 9. Magnetars. Magnetic nightmares. If neutron stars already feel extreme, magnetars push that concept into nightmare territory. These rare neutron stars possess the strongest magnetic fields known in the universe. Their fields can exceed a quadrillion times the strength of Earth's. The numbers are absurd, but the consequences are very real. If a magnetar sat halfway between Earth and the Moon, its magnetic field could disrupt electronics across our planet. Move it closer, and the field itself would start to alter the behavior of matter. Near a magnetar, atoms do not behave normally. Electrons are squeezed into unfamiliar configurations, chemical structures warp, and the magnetic field literally reshapes the architecture of matter. In 2004, magnetar SGR 180620 released a giant flare. It sits roughly 50,000 light-years away, yet the burst was still powerful enough to affect Earth's upper atmosphere. Something on the far side of the Milky Way briefly left a fingerprint on our sky. The deeper mystery is that scientists still do not fully understand how magnetars generate and maintain such extreme fields. Every answer creates new questions. It is like discovering a lighthouse whose beam can scorch worlds thousands of miles away. Yet nobody knows what powers the lamp. Magnetars remind us that the universe permits environments where matter itself becomes negotiable. The rules are not broken. They are simply operating in regimes human experience was never built to comprehend. Number 8. The hypothetical quark star. Now the ground drops out from under even that. Imagine a neutron star becoming so dense that even neutrons cannot survive. According to some theoretical models, gravity may compress matter beyond the neutron stage into something entirely new. This hypothetical object is called a quark star. Neutrons are not fundamental. They are made of quarks held together by the strong nuclear force. Under ordinary conditions, quarks stay confined inside larger particles. Nature seems to dislike letting them exist freely. But in the densest stellar remnants, pressure may become so overwhelming that neutrons dissolve completely. Instead of a sea of neutrons, the star would contain an ocean of liberated quarks, in a state unlike anything we have observed directly. If quark stars exist, they would be among the strangest forms of matter in the universe. Not a conventional star, not a planet, not ordinary nuclear matter. Something in a different category entirely. No confirmed quark star has been identified. Several candidates exist, but the evidence remains inconclusive. Our observations are limited, our experiments cannot sustain the required conditions, and our models disagree on what signatures expect. It is like trying to map the bottom of a black ocean using faint echoes. Shapes appear in the darkness, patterns emerge but certainly remain out of reach, and that uncertainty matters. If matter can reorganize into forms beyond neutrons, reality may contain entire layers we have barely begun to discover. Number 7. Cosmic strings. Cracks in spacetime. Imagine looking across the universe and finding a crack in it. Not in a planet, not in a star. A crack woven into spacetime itself. That is the idea behind cosmic strings. They have never been observed directly, but they emerge naturally from some theories of high-energy physics and early universe cosmology. Fractions of a second after the Big Bang, as the newborn universe cooled, it may have undergone phase transitions like water freezing. Imperfections in that process could have created cosmic strings. A cosmic string could stretch across galaxies, while remaining thinner than an atomic nucleus. Despite that tiny width, it could contain enormous mass and energy. A single string might warp spacetime so dramatically that objects passing nearby experience a distortion in the geometry of reality itself. Cosmic strings do not fit comfortably into our ordinary picture of the universe. They would be relics from energy scales far beyond anything we can reproduce, preserving information about conditions less than a trillionth of a second after the Big Bang. Scientists have searched for their signatures through gravitational lensing and other observations, but no confirmed detection has emerged. Still, the mathematics refuses to dismiss them. They occupy a strange space between prediction and mystery, possibilities emerging from equations that otherwise work extremely well. It is like discovering an ancient scar on reality and realizing it may have formed before the first stars existed. If cosmic strings are real, the universe may still carry physical wounds from its birth, invisible seams stretching across the cosmos, quietly reminding us that reality was forged in violence. Number 6. The center of the Milky Way. For most of human history, the center of our galaxy was hidden behind thick clouds of gas and dust. Only infrared and radio observations finally pierced the darkness. What they revealed was not reassuring. At the heart of the Milky Way lies a supermassive black hole called Sagittarius A. It contains about 4 million times the mass of the Sun in a region smaller than our solar system. Every star in the galaxy, including the Sun, ultimately orbits within its gravitational influence. The galactic center is one of the most extreme environments known. Stars race around Sagittarius A at millions of miles per hour. Powerful magnetic fields twist through space. Superheated gas collides and explodes. Radiation floods the region from every direction. In 2020, the Nobel Prize in Physics was awarded for work confirming this supermassive black hole through decades of stellar observations. Something invisible, massive, and compact controls the motions of nearby stars. Yet mysteries remain. Why do some stars orbit so close and survive? How did Sagittarius A grow so large? What role did it play in shaping the Milky Way? It is like standing in the engine room of a machine larger than imagination itself. Everything moves, everything vibrates, everything pushes on everything else. No one fully understands how all the pieces fit, and your entire civilization sits far away on the quiet outskirts. The universe did not place you at the center of anything. It puts you on the edge, looking inward toward forces you barely understand. Number 5. The photon sphere. Light in orbit. Most people have heard of the event horizon. Far few know about the photon sphere. Yet this may be one of the strangest places in existence. Around a black hole is a region where gravity is strong enough to force light into circular orbits. This boundary is called the photon sphere. Crossing it does not guarantee destruction, but entering it means stepping into a realm where light stops behaving in familiar ways. Normally, light travels in straight lines through space. Our eyes and telescopes rely on that. The universe feels understandable because photons carry information on predictable paths. Near the photon sphere, that assumption fails. Light can bend around the black hole multiple times before escaping. A single star can appear in several locations at once. In principle, you could see the back of your own head, because photons emitted behind you loop around and return to your eyes. Reality begins to resemble a hall of mirrors. Mathematics comes directly from Einstein's general relativity. Observations from the Event Horizon Telescope, which captured images of black hole shadows, agree with these predictions. The equations work, the observations agree, yet the consequences feel impossible. Imagine standing in a vast hall, where every reflection shows a different version of the same scene. Every direction holds echoes of light, trapped and redirected by gravity. Your sense of where collapses. Near the photon sphere, what you perceive as reality depends entirely on the paths light is allowed to take. Change those paths, and the universe itself appears to change, not because reality changed, but because your access to it did. That distinction is more fragile than you might like to believe. Number 4. The Planck scale. Every place so far exists somewhere in the universe. The next one may exist beneath the universe itself. To reach the Planck scale, keep zooming in. Smaller than atoms, smaller than protons, smaller than quarks. Eventually you reach a length of about 1.6 times 10 meters 3/5 meters. At this scale, quantum mechanics and gravity are expected to be equally important. General relativity describes gravity on large scales. Quantum mechanics describes particles on small scales. Both theories work. Both have passed countless tests. But when scientists try to combine them at the Planck scale, the equations collapse into nonsense. Some theories suggest spacetime here is not smooth at all. Reality might resemble a fluctuating foam, bubbling with microscopic distortions. Distances may lose meaning. Time itself might stop behaving as a continuous flow. No telescope can observe this realm directly. No experiment can reach these energies yet. The Planck scale sits beyond current technology, but every serious attempt at quantum gravity eventually arrives here. It is like finding a page in the middle of a book where every sentence becomes unreadable. The story clearly continues. The information is there. The language fails. The disturbing implication is not simply that we lack answers. It is that reality may contain layers where concepts such as distance, duration, and location stop having meaning at all. Number 3. Inside the event horizon. Black holes fascinate us, but most discussions focus on what happens outside them. The truly unsettling mystery begins after you cross the event horizon. The event horizon is the point of no return. Once something passes it, not even light can escape. The object becomes permanently disconnected from the observable universe. According to general relativity, an observer falling into a sufficiently large black hole might cross the horizon without noticing anything special. There is no wall, no flash, no visible boundary. Reality seems normal. And then it does not. Beyond the horizon, every possible future leads inward. Moving away from the center becomes as impossible as moving backward in time. Space and time exchange roles in ways that shatter normal intuition. The math continues. Our understanding does not. Quantum mechanics say information cannot be destroyed. General relativity suggests that anything crossing the horizon is lost. Both cannot be entirely correct. This contradiction has fueled decades of debate. Hawking radiation, information paradoxes, holographic principles, and ideas that spacetime may emerge from deeper structures. No consensus exists. We check the observations, we check the mathematics, we check the assumptions. The mystery remained. It is like discovering a door that can be entered but never reported from. Every theory points toward it. Every equation approaches it. No message ever returns. Number 2. The gravitational singularity. At the center of classical black hole theory lies a place even stranger than the event horizon, the singularity. If matter continues collapsing indefinitely, Einstein's equations say it reaches a point of infinite density and zero volume. Gravity becomes infinite. Curvature becomes infinite. The equations explode into impossibility. Physicists treat infinities and equations as warning signs. When a theory predicts one, it usually means it has reached its limit. The singularity is a location where our understanding of reality breaks down completely. General relativity, one of the most successful theories ever, effectively says, I cannot continue. Some researchers think quantum gravity will remove singularities. Others propose bounces into new universes or transitions into unknown quantum states. Nobody knows which, if any, is right. Imagine following a map across a continent only to discover the final section has been burned away. The roads disappear. The destination is hidden behind blank paper. That is what singularities represent. Places where mathematics stops describing reality, while reality continues anyway. Number 1. The edge of the observable universe. The last place is not a star, or a black hole, or any solid object. It is a boundary, the edge of the observable universe. Every night sky humans have ever seen, every galaxy ever photographed, every neutron star, every planet, every atom in your body exists within this cosmic horizon. Beyond it, we do not know, because the universe has existed for about 13.8 billion years. Light has had only a finite time to reach us. There is a limit to what we can observe. Beyond that horizon, regions of space remain forever inaccessible, not because they do not exist, but because their light has never arrived. The observable universe spans roughly 93 billion light-years in diameter, yet cosmology suggests the entire universe is vastly larger, potentially infinite. If so, everything we have ever seen is a tiny fraction of reality, a microscopic island in an unimaginably larger ocean. Beyond the horizon, there are almost certainly more galaxies, more stars, more planets. But perhaps there are different cosmic structures, different initial conditions, even regions forever disconnected from us by the expansion of spacetime itself. The terrifying part is not what might exist out there. The terrifying part is that we may never know. Some boundaries are built into reality itself. Some horizons cannot be crossed by any technology. It is like standing in a vast cathedral illuminated by a single candle and realizing the darkness beyond the light is not shrinking. It is expanding. The edge of the observable universe is not the edge of reality. It is merely the edge of our access to reality, and those are not the same thing. Tonight we traveled across some of the strangest places in existence. We stood on the surface of neutron stars where atoms cease to exist. We entered the magnetic nightmare of magnetars. We explored hypothetical quark matter, cosmic strings, and the violent heart of our galaxy. We followed light into the distorted geometry of photon spheres and descended toward scales where space and time may lose meaning. Then we crossed deeper thresholds, the event horizon, the singularity, and the observable edge of the cosmos. At first glance, these seem like separate mysteries, different objects, different problems, different branches of physics. But perhaps they are all pointing toward the same conclusion. The universe is not breaking, our understanding is. Again and again we encounter places where our equations become incomplete. Repeatedly, reality reveals layers more complex than we expected. Nature keeps reminding us that the map is not territory. We are a young civilization on a small planet orbiting an ordinary star near the outskirts of an ordinary galaxy. Yet somehow, we have managed to glimpse the edges of knowledge itself. And what waits there is not certainty, it is mystery. The most honest words in science remain the most unsettling. We do not know. If those words keep you staring into the dark a little longer tonight, wondering what else hides beyond the reach of your light, you already know where to go. The universe does not send reminders, but Astro Buddy does. Subscribe, and we will keep pulling back the curtain together, one terrifying truth at a time.